So, let's speak a bit more about time series statistical models. The purpose of the course is to develop and study theoretical time series. So the idea is the more we develop our understanding of the theory behind the data production process, the smarter the things we will be able to say about the observed data sets. So just to give an example of a sophistication which is actually quite easy to reach once we've studied all this, is the very interesting and important question of understanding change point. So we won't be doing this in this course, sadly, but it's a very natural topic that comes right after this course, and the course that we'll be having together. Is that let's imagine that we understand the data production process which gives us the data. And so we understand the series xt, we understand its mathematical properties. But then we observe one realization of this process. My drawing here is really awful, sorry. We observe one realization of the process which behaves a bit like this, something like this, and then something like this. And we see that there is some kind of different behavior between this part here and this part here. And a very important question would be to understand, is there at some point in time, let's say t0, is there a break in the model? Is the model different after this time than it is before? So we want to be able to detect a change point. Well, in order to be able to do this, we have to have a good understanding of the properties of the model, and to do what people do in statistics also is to say, well, if there had not been a change in the model, well, then we would not have been able to see this kind of change in the volatility, and then we would have been witnessing an unlikely event. So with our understanding of the model, we can say very smart things. For example, we can detect change points in the models. In order to say smart things, well, we need definitions. At least as a mathematician, I am happier with definitions. And the first definition, which all mathematicians know, and probably a lot of you know already, is that of a stochastic process. So we are dealing with stochastic processes, and a stochastic process is nothing else than a collection of random variables indexed in time. Indexed in some set t, which we associate to time. It's a collection of random variables which, moreover, are all defined on a common probability space omega AP. So all the random variables are supposed to belong, are supposed to be descriptions of related objects. So they are supposed to live on a common space, omega AP. So omega being the sample space, A being the sigma algebra, and P being the probability measure. So most of you, I guess, are very familiar with all this. Those of you who are not familiar, it won't really play a role, so don't worry so much. We won't be using any fine properties of sigma algebras. It's not financial mathematics, so we're not going to be doing filtrations or integration with respect to stochastic processes. So we have a collection of random variables defined in a common probability space, and given one omega and omega, the functions which associate to time the evolution of the xt's are called realizations or trajectories or sample paths of the process. So let's maybe give an example. So let's say that xt is are, well, I mean, even take a simpler index set. So let's say that each xt is 1 or 0 according to coin toss. Well, then this is what? It's a collection of random variables which live on 0, 1. So we have x1, we have x2, we have x3, we have x4 up to x10. Each of these can take the value 1 or 0 according to a coin toss. We imagine that we have 10 coin tosses, which we take to be independent. Well, there are 2 to the power 10 possible outcomes, which we collect into the sample space omega. The sigma algebra is just the collection of all possible parts of omega, and the probability measure is just a uniform probability measure. And one realization of this would be, for example, if we had observed the results, let's say a sequence of heads followed by tails 5 times followed by heads, well then we would have had 1 1 0 0 0 0 and then 1 to conclude. Another possible realization would be heads, tails, and so on. Heads. Well, then here we would have had 1 0 1, and then so on up to 1, and so on. For each possible realization, we have a different sequence of values, and the function which associates to t the value of xt evaluated on the omega, so the well, either the orange or the red curve in my drawing. Well, that is called an observation or a sample path. Typically, I will use a notation capital X to denote the random variables, and then little x to denote the observed values. So xt of omega in my notations, well, xt of omega is denoted little xt. Okay. The collection T over which my random variables are indexed is, well, it's an index set, and we typically identify this with time, although it's not always necessary. And in the literature, well, you have either an integer or positive integers or just integers, and you could also have continuous positive time or continuous time in real time. In this course, we will be exclusively working with so for the models at least, we'll be working with the indexed in integer time. So here, that's what it's, well, you all know what the integers are. So it's this set here. Well, this would be the future. This would be the present, and this would be the past. So we have a sequence which has a future, a present, and a past. And that distinction is made possible by the fact that we have an index set which is, let's say, by infinite, although that makes not much sense. Whereas if we only had the integers, well, then we'd only have a future. Okay? So, how do we construct time series models? Well, let's have a look at the variety of prototypes. So how many of you? There's 34 left. We've lost a few people. Let's have a look at example 1.1. Well, 1.11, sorry. So some models. The first model is the simplest. It's what we call the IID sequence, in which the xt, the process, is a sequence of IID random variables. In that case, I will often use the notation xt tilde IID, and very often I will use the notation tilde IID mu sigma squared to indicate that all these guys have mean mu and they all have variance sigma squared. So what would an IID sequence look like? Well, it would be a sequence which has no clear structure, nothing. So the random variables bring no information onto one another. So it could be typically something like this. If we looked at the evolution in time, nothing. Well, my drawing is probably not very good. But there is no, it looks like just noise around a given value mu. There is no clear evolution in time. The variance seems to stay the same, and there is no clustering of any kind. Okay? So an example would be xt would be IID. Normal would mean 0 and variance 1. That's a collection of independent identity distributed random variables. Another example would be xt, which would be a Poisson of mean lambda. Another example could be xt, which would be, well, take any distribution that you like and you can construct an IID sequence with this. So just be careful that these guys do not have the same behavior. This is a sequence of continuous random variables, so continuous state space. This is a sequence of binary random variables, a sequence of zeros and ones. This is a sequence of integer valued random variables, and so on. So the trajectories would not be looking, would not look similar. Okay. From an IID, so the IID sequences are basically the building blocks of the whole theory. From an IID sequence, you can construct, for example, a random walk, which will not be the objects that we are going to study here because random walks do not behave nicely. But they can be constructed quite nicely. Well, they can be constructed quite easily. Let's begin with an IID white noise sequence. Well, an IID sequence, sorry. I haven't defined what white noise was yet. So this is a sequence, and then we define xt from zt as what? Well, xt is 0 if t is 0, and then it's the sum, so still t is in the integers here, and it's the sum for k going from 0 to t of the zt's. Zk, sorry. And maybe I start at 1, otherwise I would have a problem. And t is in z0. Okay, that looks good. We could take this, maybe we can add some trend. So let's have a look at this. Voila. So we could take this. So what would that look like? Well, imagine that the zk's are IID IID Bernoulli with parameter 1/2. What does that tell us? It tells us that these guys are either 0 with probability 1/2 or 1 with probability 1/2. Well then, let's take delta is equal to 0 in the whole sequence. In all my illustrations, I'll take delta is equal to 0 because it's not so enlightening. Well, if the zk's are Bernoulli with parameter 1/2, the xk's or the xt's are what? Well, they are sum for k going from 1 to t of zk's. They belong to, well, if all the zk's are 0, they could be 0, or they could belong to 1, or they could belong to, and it goes up to t. Well, then xt itself follows a binomial distribution with parameters t 1/2. Is that okay for everybody? That if the zk's are IID Bernoulli, the sum of the zk's would be a binomial. Are you still awake?
Yes.
Okay.
Yes, that's clear.
Okay, great. So we have the distribution of the xt's, but of course the xt's are not independent. Because if I'm given xt minus 1, I know that xt is just, it's xt minus 1 plus an independent noise, which would just be a 1 or a 0. So xt given xt minus 1, it's just xt minus 1 plus some independent noise. And this gives me something that looks a bit, well, how would it look? Well, if I wanted to draw this, I start in 0, then if next step, let's say I get a 0 again, then I go to 1, 1, 1, I get 3 zeros in a row, then I could have something like this. So it's something that looks a bit like this. So at time t, xt follows a binomial, but the evolution is very, very strongly dependent on the previous observation. That would be one kind of random walk. Another kind of random walk, which would be perhaps less typical. Oh no, let's do another one which would be typical. It would be the Rademacher. So maybe you don't know what the Rademacher distribution is. So it's either a 1 with probability 1/2 or minus 1 with probability 1/2. Let's do the same construction. Well, it won't be a binomial distribution anymore, but it won't be very different. So then we'd have a random walk which could go something like this. So if we have, let's say, we start with a +1, we go here, then we have a sequence of 3 -1s, we go down here, then we go back up here, and so on. We'd have trajectories which would look a bit like, well, more like what you'd expect from a random walk. Another example that you could take would be to take the zk's, which would be IID normal. But then in this case, it's a bit weirder because your drawing would be, so you start, of course, in 0. But the next step you could be anywhere in the real line here. The next step you could be anywhere here. And it would be something which would be much more jumpy. Like this. So here at time xt, the distribution, so let's see if you're still following. If the zk's are, sorry, I'm misindexing my random variables. If the zk's are IID Gaussian with mean 0 and variance 1, xt has what distribution at time t?
Sorry, I just missed one thing. What's the distribution in the photograph above?
Don't really know. It has a name. That's why I didn't ask it. It's the distribution.
Oh yeah, okay. Okay, but what did you write? Like that starts with an R. Like
sorry, the name here. That's Rademacher.
Okay.
It's one of the so it's one of the binary random variables, which is very, very useful. So you have the Bernoulli, The Bernoulli, of course, everybody knows, it's either 0 or 1, and the Rademacher is the equivalent of the Bernoulli, but it's -1 and 1.
Okay, great. Thank you.
So it's also a coin toss, but instead of having 1s and 0s, you have 1s and -1s. So if the if the zk's are now normal, the distribution of the xt. So those of you who studied maths, you should know this very, very easily. The other ones you should be. No, it's not a chi-squared, if that's what you mean. It's much simpler. You have a sum of independent Gaussians. Well, you know that the sum of independent... Yes, Céline, it's just normal, because it's a sum of independent normals. It's normal with mean what? Well, 0. Yes, thank you, maths students, and variance t. But the distribution of xt given xt minus 1 is now going to be, let's see, what would be the distribution of xt given xt minus 1? That's more, no, Henry, because here xt given xt minus 1, well, xt given xt minus 1 is just xt minus 1 plus zt. So now this guy here is fixed, we consider him fixed, and we add him some random noise, which is itself Gaussian. So given xt minus 1, xt is, it's a bit more complicated question. It's going to be Gaussian again, with mean xt minus 1, which is considered fixed, and with variance 1. I don't know if that's clear. For everybody?
Yes.
Okay. So all this to say what? Well, all this to say that if I give you a random walk, well, even inside the random walk, you have quite some wealth in the construction that you make, depending on what you're adding. If you're adding Bernoullis, you have binomials, but then you have some kind of process of a certain form. You see that this guy here can only increase, for example. He can only go upwards, whereas this guy here can go up and down. So with the Rademachers, you can go up and down. With a certain kind of jumps. With the sums of Gaussians, you can go up and down as well. The jumps will be Gaussian, and so on, and so on, and so on. So random walks are fascinating. One of the most fascinating ones would be this one. So if you like this kind of stuff, I would advise you to go and read the book by J. Michael Steele. Foundations of Stochastic Calculus. I think that's what it's called. If I remember to do it, I will give you the PDF. And he has Evo, no, don't memorize. Memorize as little as possible. It's impossible to memorize all this. It's much better to understand. So if you find parts of what I'm talking about too difficult to understand, so for example, if you have no idea, I'm not specifically talking to you anymore, I'm talking in general. If some of you have no idea what I mean with this, if you just think I'm speaking Chinese or Japanese or Irish, please send me an email in private if you don't want to stop the class. Send me an email in private and we can take the few minutes it will take for me to help you to understand what I mean with these notations. Perhaps you don't know what I mean by this notation here and then you're really, really stuck. Ask me and I'll take the time that is needed to help you understand. Memorizing is, well, if you're blessed with a good memory, and good for you, but I think memorizing is never good. So back to my little rambling here. This process here is actually quite fascinating because well, it has nice intriguing properties which are well worth studying, and this guy is very closely related to Brownian motion. For those of you Brownian motion, for those of you who have studied that kind of stuff. All these guises are related to Markov processes, for those of you who have studied this kind of stuff. They're quite interesting to study. But they won't be the topic of this course. They are a different topic entirely. So we will basically exclude them as soon as we can. Another kind of process that we will be studying in quite some detail are the so-called moving average processes. MA of Q here. And a moving average process is once again constructed from white noise IID sequence. So we take ZT IID once again. With mean, what did we take? With mean some mean, and with variance some variance. And now instead of just summing the ZTs, we say that XT is, well, I'll take maybe a simpler example than what I've talked about in the slides. We could take XT is ZT plus 1 plus ZT plus ZT minus 1 divided by 3. So this is what? It's an average of the ZTs over a window of length 3. So what's going to happen with this guy? Well, this guy, well, you have your sequence of ZTs, and then you take an average. So let's imagine that the ZTs would look something like this. So they are, of course, they are just white. They're just noise, so there's no specific structure. And then you're giving some structure by looking at the average, well, over these 3, then the average over these 3, then the average over these 3, and so on. I guess you get the idea. As the time passes, you look at averages. So this would give you x1, this would give you x2, this would give you x3, and so on. And what's going to happen if you look at the xt's rather than the zt's? Well, it's going to be following basically the same kind of behavior as the zt's, but with somewhat less volatility and a little more smoothness. So my drawing is not good at all, I'm sorry, but I hope you get the idea. You have some kind of smoothing effect. So smoothing, my writing is really awful, I'm sorry. Oh, I think I forgot to launch the, no, I am taping. So just a note on the side, I typically forget to start the video. So please, if you realize that I haven't started the video, ask me to start it. So why is this called a moving average? Well, because you're taking an average with a moving window. So that's just, that's why it's called a moving average. And more generally, you could consider moving averages of the form, sum for j going from, well, what did I use in my notes? J going from 1 to q of a j z t minus j. So where the aj's is some fixed sequence of weights. Well, these moving average processes we will be studying quite a lot, because as we will see, they are building blocks of our theory. Another sequence that you can make from white noise, which will also be very important for us, is the autoregressive processes. And that's, so I will just give an example of autoregressive of order 1. We will be doing the autoregressive of general order later on. So the autoregressive processes are processes which are self-referential, let's say. So again, we start with ZT and IID sequence with some mean and was, let's say, mean 0 and variance sigma square, and we say that xt is in fact defined as a multiple of the previous guy. So we take rho times xt minus 1 plus zt. So what we say is that the evolution is you start somewhere. You start with xt, with x0. Let's say that x0 is here. Then x1 will just be a certain multiple of x0. So let's say, let's imagine that rho is less than 1. And then to this we add some noise. So let's say we go here. And then we again take a multiple and then we add some noise. And then we go here. And so on. So x1, x2, x3, and so on and so on and so on. That's another way of constructing a process which would now be self-referential. So it would be autoregressive. You're doing a regression. Xt is made by a regression onto the process itself. Another way of constructing a sequence is signal plus noise. That's also a very important component of the time series process. So again, we start with noise sequence. With some, well, we'll take mean 0 and variance sigma squared. And we consider xt to be a certain function, which itself is not random at all. It's just a certain function, mu of t. And then to this function we add some noise. So it's a deterministic function. So here, very important questions that we are not going to deal with, but which are quite fascinating, is, for example, given xt, can we reconstruct mu? So we observe, what we observe is a noisy process. We observe this. Can we deduce the noiseless process from the noisy process? Well, you can say that depends on the noise. Of course, it does depend on the noise. So let's look at an example here. So here I took a cosine wave. I took just cosine. Oops, sorry. I took cosine. Well, I took this wave. So that's the wave in yellow. Here. And then to this I added some noise. So the first expression is the yellow one. Here. That's the yellow plot. And then I added some noise. So I added a normal noise. With variance, well, it seems that I just added the variance 1. So here, well, what you see here in the purple plot is that you can still distinguish the wave. You can still distinguish the cosine wave. Here it is. I put it in yellow. You can still distinguish it here. It's just that it's been noised, and so on. And then in the next level I added a noise with variance 25 here. So that's the purple one, and next level is the blue one. And here, well, clearly I've added so much noise that you can barely distinguish the cosine wave that's in the middle. Okay. Well, that's just signal plus noise. So in my example, mu of t is just, what is it? It's cosine of cosine of 2 pi t divided by 50 plus 0.6 pi. And then I added some noise. Okay. And then the last example of very famous and useful stochastic process, but this one again we won't be studying it, it's a different topic. It's the so-called branching processes. So that's so random walks will be more important in let's say finance. Those of you who would have studied stochastic calculus will have studied random walks in quite some detail. Moving average, autoregressive, and signal plus noise are basically the objects that we'll be studying in this course. And then another example which is very important in epidemiology, but I think nobody's studying this anymore at ULB. It used to be people like Guy Latouche, but I think Guy Latouche is not working here anymore. And I don't think anybody's left. They've all retired. But it's quite a very rich topic. So I know Thomas Bruce, some of you might know Thomas Bruce, he's still here quite often. He was a specialist of branching processes. And this stochastic model is used to describe the evolution of a population size. So here we still have, it's a much more complex process. So let's see, how do we do this? We imagine that we have certain original, let's say Adam and Eve in the Christian tradition. And these guys will have, so we have the original, they will have a certain number of babies according to a certain distribution. So let's call this Z Z1 at level 0. Z10, well, they give a certain number of babies at level 1 of the population. So we have level 0, then we have level 1. Each of these babies born at level 1 will then itself give a certain number of offspring. Let's say this guy gives a certain number of offspring, this guy gives a certain number of offspring, and this guy, and so on. So this will give us level 2. And then we continue up to level K, in which case we would have a certain number of offspring. A certain number of these may die, and so on and so on. And then we would be interested in the random variable xt, which would be what? Well, we sum up to at each level. So here we have z 1 up to z4 1, and then and so on and so on and so on. At each level t, the number of person present in the population is made up by, you look at all the offspring generated up to by all the persons present at time t minus 1. So each of these guys is the number of offspring generated by the element k of the population at time t minus 1. And then to each of these guys you associate a random distribution. Each of these guys has a certain law, and then this gives you a certain evolution of a population, which is itself far from trivial. And understanding the behavior of branching processes is, well, I guess you can see why this kind of this kind of stochastic process would be important, because it would be interesting to be able to understand how this evolves in time. Does the population explode? Does the population decrease? What happens if at a certain time we induce a shock? So we say every certain time there's a shock in which a certain number of these guys dies. What happens to the population? Does the population survive the shock? Does it not survive the shock? Well, without going into things that are too depressing, we can actually understand quite easily why this kind of process would be important. Okay, so these are 1, 2, 3, 4, 5, 6 examples of processes which are important for the theory. But of course we can imagine many more. And the whole theory is the theory of stochastic processes, which well, we will only be studying a very specific aspect of. Okay, so the building block of the entire theory is the following. It's the definition that will be coming up all the time. It's what's called white noise. White noise, it's a sequence of data which has no real structure. So this definition you have to know, it will be coming back all the time. So you probably already know it for a lot of you. White noise is just a sequence of data which is finite variance, fixed mean, and uncorrelated. Finite variance, fixed mean, uncorrelated. It's also often this, so this definition here is, this definition is often called weak white noise by opposition with an IID sequence, which would be strong white noise. It will be useful for the sequel to keep the definition as weak as possible, so not to impose independence. As you can see here, we do not impose independence, so this is not the same as independence. We only impose lack of correlation. Why? Well, although in most applications we'll be looking at strong white noise, it is generally not necessary to impose independence, and it's smarter to keep your theory as general as possible. If we have the time, we'll be discussing Garch models at the end of the course, and these Garch models would be non-IID examples, so it will be useful to keep the theory as general as possible. Because we do not impose correlation, the distribution of the marginals can actually be very different at each time point. For example, figure 1.10. Sorry, I forgot that I had given a drawing. I'll go back to this later. So in figure 1.10, what we see is that we have a sequence of white noise which is made of a certain distribution up to a certain time point, and then another distribution after a certain time point. So here it's it's before time 100 it's normal, and after time 100 it's binomial. Well, this is, here they are IID, here they are IID. Well, that's the sequence of white noise, but we see that it doesn't have the same distribution all the time. So I had forgotten that I had made a drawing of the moving average here. So the drawing is here in figure 1.9. That's the white noise process, and that's the 3-point moving average, the effect of a 3-point moving average on the white noise. And what we see is exactly as I had told you, we see a kind of smoothing. So it follows the same basic curves, but it's a smoothed version. So some of the faster oscillations are taken out, and we see more the slower oscillations in the data somehow. Okay. final definition is some kind of white noise that would be particularly useful is the white noise which is itself jointly Gaussian, so Gaussian white noise. That's in the case in which we suppose that the ZTs are jointly normal. If the ZTs are jointly normal, well then of course uncorrelatedness is equivalent to absence, so to independence. But you must remember that correlation of x, y being 0 is equivalent to x being independent of y if and only if, so this is true, if and only if x and y are jointly Gaussian. Okay? Are you still there? Because I've been speaking for quite a while now and I haven't inquired as to your well-being. Yes? No questions so far?
Question.
Yes?
Just to be sure, because I didn't follow quite well during the smoothing average part. It's just when we swap like the average from the original data that we have that kind of smoothing average curve.
I didn't understand your question, sorry.
I didn't follow quite well when you explained the first time the smoothing average from the moving average example. It was just to be sure that I understood properly.
Okay, so maybe I'll just make the...
Yeah.
So here we have the, we have the white noise, the XTs, well the ZTs in this case. And here the xt, so xt, it's zt plus zt minus 1 plus zt minus 2 divided by 3.
Yeah.
So each time point here, so it's of course it starts with a delay of 3. I think my graph is too, you don't see it of course, but I should have made it more obvious. But each time, so this here is in fact equal to the average of this guy, this guy, and this guy.
Okay, yeah, thank you.
And that's why it follows the same behavior, because of course the average is very closely related to the data of which you're taking the average. It's a very non-robust estimator, but it smooths out some of the swings that you see. These swings are smoothed out.
Okay, thank you.
Peter, any other questions? No? Everybody's happy? Okay. So now we have defined, so we have not much, we haven't said much for the moment. We've defined the stochastic process. We've given a few examples of stochastic process which will be used in this course. So IID sequences, random walk, moving average, autoregressive, signal plus noise, branching processes. We've defined, and it's in a very technicolor way, what's called white noise. So that's just a stochastic process which is fixed mean, fixed variance throughout the process and absence of correlation. And the particular case of stochastic of white noise, which will be often used, and that's something that will be quite annoying when you'll be going on the internet, is that it won't often be clear if the references you're using on the internet make only reference to Gaussian white noise or not. But so in this course we use weak white noise by opposition with strong white noise, which only requires independence. But there is also white noise, sometimes called white noise, but it's Gaussian white noise, in which case you're supposed that ZTs, so the noise sequence, is jointly normal. But of course, because in the Gaussian case correlation is equivalent, well, independence is equivalent to absence of correlation, Gaussian white noise is also IID white noise with Gaussian innovations. Okay, So the next definition, which is an important process, again, we won't be really working with this in this course, but it's an important process that you need to know. So for those of you who have never seen it, I introduce you a very important process. It's the Gaussian process. And a Gaussian process is a stochastic process which is Gaussian, not in the sense that the xt's are themselves Gaussian. That's very vague. So we're not talking about the marginal distribution. We're saying that globally the process is Gaussian in the sense that any combination of any observation at any time point is itself Gaussian. So the xt's are Gaussian, but also the linear combinations of xt and xs is Gaussian, and also a linear combination of xt, xs, and xk, and so on. Any linear combination of any collection of variables extracted from the process has to be itself Gaussian. So it's much, much, much stronger than requiring only Gaussianity of the marginals. Now, since the law of a Gaussian process is, of Gaussian vector, and therefore a Gaussian process, is entirely identified, I see there's a typo here, is entirely identified through its mean as covariance. Well, one way of characterizing a Gaussian vector is to define the mean, but it's not a mean anymore, it's a mean function. And it's also define the covariance function, gamma of Ts. Not so obvious is that any Gaussian process defines a specific mean function and a specific covariance function, and vice versa. Any covariance function, gamma, and any mean function define a Gaussian process with that mean and that covariance. That's something that we will be seeing in the proof of theorem 1.38, but seeing the speed at which I'm going today, we will not get there today. Okay, I think that's all I have to say about this. Those of you who know about Gaussian processes know how important this is. And those of you who don't know about Gaussian processes, well, it's not in one slide that we will be saving you today. Okay. I'm sorry, but I really need some sugar, so I'll go and get some sugar, and I'll be right back. Let's take a 5-minute break. I'll be back in 5 minutes. Okay, sorry. I've been teaching since this morning and a bit tired. So I'll be eating while speaking. Still there?
Yes.
Yes.
Great. How many of you are there left? 33. You're quite resistant. So, yeah. Evo is still alive. I'm barely alive. So, before going into the specifics of time series, let's do some rather general theory. You won't be needing this, at least not really, because we'll be dispensing with it. But it's and I think we'd stop with that for today because it's already 5:13. It's a section that describes the theory behind what we're going to be doing. And this theory is actually quite complicated, but we are lucky that a certain Kolmogorov, I'll give you the link to his Wikipedia page. Well, he basically solved the problem for us. So we can say thank you very much, Mr. Kolmogorov. Good question, thank you. Is the recording on? Yes, it's still on. So this guy Kolmogorov, you're very much invited to go and look at his Wikipedia page. He basically proved that what we are doing, well, what we are going to do, makes sense. Because it's not because you write something that it's true. Although in this post-Trump era, you might be thinking that well, some people believe that because it's written, it's true, or at least because it's written. Yes, the recording is on. Voila. Because it's written by somebody that they believe in, that means that it's true. In general, that's not true. And as a scientist, you must always be aware that what you're making actually makes sense. It's not because you like it that it's true. So, for example, so section 1.3. I wrote this. Let's call another regressive process of order rho, of order 1, this thing here. So we take xt as rho times xt minus 1 plus epsilon t. And I actually made a little drawing, you must remember. We start somewhere, then we jump, and then we add some noise. And we go here, then we jump, and we add some noise, and so on and so on. Well, is that process always defined? Well, let's have a look at an example. Let's say I want xt to be twice xt minus 1 plus some noise. Okay, well, if that is possible, well, then it also has to be possible at level xt minus 1. So xt minus 1 would be twice xt minus 2 plus some noise at time xt minus 1. Is everybody happy with this? But then if that's possible, this should be 4 times xt minus 2 plus twice epsilon t minus 1 plus epsilon t. But if that's possible, then it should be also, am I right here, 8 times xt minus 3 plus 4 epsilon t minus 2 plus 2 epsilon t minus 1 plus epsilon t. And I guess you see where I'm going. This is in fact equal to the sum for t going, so for j going from 0 to t of 2 to the power j epsilon t minus j plus 2 to the power No, not to the power t. It goes from, I can go up to any level. So let's say n to the power n xt minus n. Is that good? Am I correct? I guess I am. But this is also valid for any n. So if I want, I can let n go to infinity. But if I let n go to the infinity, I'm in a very strange situation, because this does not converge. It becomes infinitely large. If xt minus n is not 0, well, then this becomes something very strange, and this is not a good process. Do you see the problem? Yes? No? You still there?
Yes, yes.
So why should convert? Well, because that's an excellent question, Lisa. If I write this, if I define this guy, and if I want this to be valid for all t, because that's the way I want to define it, well, if this is true, this guy here, well, then this must be true as well, and therefore all these steps must be true as well. So for any n in the integers, my process has to be, my xt has to be equal to this. Because if this is true, if it's true for one n, it has to be true for all n, and therefore this has to be always true. You get this? But then, if it's true for all n, you also have to be allowed, there is no reason why we should not be allowed to let n go to infinity. But if n goes to infinity, we are in trouble. We have a problem. Our definition is not good. You see? So, it's not because we can write it. So, of course I can write this. But it's not because we can write it that it exists, or at least it does not give us problems. A question more generally is, so now this is more for mathematicians. I mean, I've written this many times. ZT is IID noise. ZT IID, for example, normal 0 sigma squared. Okay, can you build me a space on which that guy exists? Does there exist a sequence of IID normal 0 sigma squared random variables? If t is integer, yes, that sounds quite clear. But if t is in the real numbers, so if an integer sequence sounds okay, but a real sequence indexed in real time of normals, can I build a space on which this exists? Well, it's not. I mean, it's already not an obvious question to ask, but it's even a less obvious question to answer. Do these things exist? Well, I don't know. It's not so easy to answer or even to understand. I mean, what kind of, for those of you who know about this, what kind of sigma algebra do we put on the space on which we're going to ask questions about these guys? I mean, for example, if we want to know what's the probability that ZT greater than 3 for all t, no, maybe, let's ask something a bit more smart. Let's define, so you're looking at a process which interests you, and you look at tau, the infimum of over all t's, so that zt is belonging to 5, 7, for example. And you would wonder, what's the probability that tau is greater than 3? Well, is that even an event? Are you even allowed to construct the sigma algebra in which you'll be able to compute these kind of stuff? Well, that's far from clear. And so more generally, we have to talk about what's called the distribution of a stochastic process. So you may or may not recall from your probability classes. So, sorry, I'm eating sugar. Some of you come from the maths department, so for you this is very easy. Some of you come from Solvay or from engineering schools, so this should also be very easy. For those of you who have a vaguer mathematics background, again, don't worry too much. You can understand the rest of the course without really understanding this, but it is a fundamental part of the construction. So, to describe the law or the distribution of a single random variable, what you need is its cumulative distribution function. The way you describe a random variable is you describe the function which associates to a real value x or a vector x the probability that x is less or equal than little x. And if you're in a real random variable, well, this function is non-decreasing, right continuous, bounded between 0 and 1. That's one of the fundamental results of probability theory. And another very fundamental result, which is called the you could call it the Score-Rod existence theorem. It says that if I give you any CDF f, so any right continuous function bound between 0 and 1, there exists a random variable x whose distribution is given by f. So this tells you what? It tells you that so a little aside, some people are fascinating. There's a note on my door saying teaching in progress, do not disturb, and they still open the door. Anyway, it's a different story. So what does it tell you? It tells you that in order to understand univariate probability distributions, well, what you need to understand is non-decreasing right continuous functions bounded between 0 and 1. That's it. If you have a random variable, you have one of those functions, and if you have one of those functions, you have random variables. The fact that this, given a CDFF, there exists a probability distribution, probability space harboring a random variable whose distribution is given by f, is actually quite fascinating. You may or may not remember this result. If you don't, well, it's really worth revising. It's the basis of all simulations, in fact. So if f is a CDF, so that's what? It's a right continuous non-decreasing function such that f of x is between 0 and 1 for all x. Well, if this is a function, so this is a purely analytical result. This is a purely analytical condition. There is no probability in here. No probability in here. Well, the result tells you that if the f is a CDF, then there exists a probability space, omega, equipped with its sigma algebra and its probability measure p, such that f of x is this probability. And even better, we can have this probability space explicitly, because you take omega to be, you take this to be 0, 1, equipped with the Borel sigma algebra on 0, 1 and the Lebesgue measure, and you say that x is just f minus 1 of omega. then x will be distributed according to f. So for some reason I'm writing all this in blue. I'm sorry, I'll go back to black. Well, so in one dimension we know everything. It's quite an easy theorem that you can prove in first year, probably the courses in, at least for the math students. For the engineers, well, you use this you all use this when you're performing simulations. So for example, if you go into R and if you want to simulate an exponential random variable, well, what you do in R, you just go, let's see, I open my R Studio. You can't see what I'm writing, but it doesn't matter. And then I think it's type, you type in rexp, and then what? You say how many you want, and then you give the rate at which you want your, say you want the rate of your exponential distribution. And if you type this, what will it give you? It will give you n realizations of, so n independent realizations of a random variable distributed according to an exponential distribution with parameter lambda. And what does R do? Well, as you can see, it's R, or I think it's in Python or in any other language. What does it do? Well, it simply, concretely, what does it do? Well, it generates n numbers which are uniformly distributed on 0, 1. That's what's here. It's uniform experience with distribution on 0, 1. And then it's, so this would be u1 up to un, these guys. That would represent what I've put in blue here. And then it simply computes what I've written here in orange. It simply computes x, which is given by f minus 1 of the uniforms. And then it computes f minus 1 of u1, f minus 1 of un, where, well, f of x is a CDF of an exponential distribution. What's the CDF of an exponential distribution? Where it's 1 minus exponential of minus lambda x, indicator of x greater than 0. So f minus 1 of u is what? Well, it's, you want 1 minus e to the power minus lambda x to be equal to u. So 1 minus u is e to the power minus lambda x. So ln of 1 minus u minus this divided by lambda is x. So the inverse is minus a logarithm of 1 minus u divided by lambda. So what does R do? It does nothing very smart. It simulates uniformly distributed numbers on 0, 1, these guys. And then it simply computes minus log of 1 minus these guys divided by lambda. And the theorem guarantees that, so if I call that guy x1 and this guy xn, x1 and xn behave as if they had been generated from an exponential. Does this ring a bell for everybody, or is this new? Okay, it seems a bit new. Okay, it's not important for this course, but so that's the way your computers generate numbers. Well, it's one of the ways, because it's actually much more complicated. But the very beginning is that this theorem here, Skorrod, is the basis by which you know how to generate random numbers with a given probability distribution. Okay, and maybe I'll give you a proof of the theorem. So the proof of the theorem is what? It's that, let's suppose that f is, I'll make my life very easy. I suppose that f is a strictly increasing CDF, which is continuous on R, and let's suppose as well that the limit at minus infinity is 0 and the limit at plus infinity is 1. An example of such a CDF would be the CDF of normal 0, 1 when the variable. That's a nice strictly increasing, very soft, gentle CDF. So what does this look like? Well, it looks like something like this. So it's increasing, continuous, and then it looks like this. That's 1, that's 3. Now, let's say that u is a random variable that's uniformly distributed on 0, 1. Okay? I claim that x, which is going to be f minus 1 of u, I claim that this guy will be distributed according to f. What does that mean? Well, in order to check this, we need to check that the probability that x is less than or equal to little x is f of x for all x. But by definition, the probability that little x, capital X is less than little x, well, capital X is this guy, this is this guy. So I simply replace. So now I've just replaced. But if my function f is strictly increasing, continuous, limit 0, limit 1, Well, then I can simply say that the probability that f minus 1 of u is less than x is the same as the probability that u is less than or equal to f of x, because if f is increasing, the switch does not change the order of the inequality. Yes, but by definition, if u is uniform on 0, 1, this is equal to f of x. Therefore, I'm finished. Okay? So all this to say what? Well, all this to say that, so for those of you who didn't follow, don't worry too much. It's not really the topic of this course, but it's an interesting thing to know. It's said for random variables or even for random vectors, everything is covered by our understanding of the cumulative distribution function. We know what happens, we know how to generate, we know everything. However, things are much, much more complicated when processes are concerned. Because here what? Well, we don't need to model only the behavior of what happens at time t. We don't need to only need to model the xt's. We need to model the whole joint behavior of the family. So we need a whole family of xt's, and we need to understand how they behave together. We stressed that the marginal distributions, so the distributions of the xt's, so for example here in my drawing, where was it? So here the distribution of the xt's, this guy, this guy, that does not suffice to understand joint behavior. The distribution of the marginals tells us nothing about the dynamics of the process. Okay? A very, very striking example of this is that if I say that xt is IID normal 0, 1, or if I say that xt is x, which is itself IID normal 0, 1, well, this guy, well, maybe I should call this x tilde, then xt and xt tilde have the same marginal distributions. But of course, this guy is much more complicated than this guy, because the xt tilde is just a repetition of the same x. So if x is 3, xt tilde is constant. It's always 3. So this guy, if I draw him, he's just going to be constant. It's x1 is x, x2 is x, x3 is x. It's a constant process. Whereas this guy here, his trajectories will be random like this. But of course, at any fixed time t, this guy has the same distribution as this guy, because both of them are normal 0, 1. So it's not only the marginal that we need to understand, we need to understand the whole behavior of the process. Here's an example of 4 different time series which have the same marginals. And we see that they don't look alike. This guy does not look like this guy, which does not look like this guy, and does not look like this guy. So we need much more than simply the distribution of the marginals. And for this, we need the following definition. We need the distribution of all the, so we need the distribution, all the possible joint distributions at the same time. And that has a name. It's called the finite dimensional distribution, the FDD. So it's the equivalent for processes of the CDF for variables. Okay, let's have a quick inquiry. Who's still alive? Who's still following? Good idea. Okay, so you're still there. Jonah, kinda. Okay, I'll continue with this section. I'm so tired I can barely understand myself now, but I'll continue with this section, and we'll finish with this so that we're rid of it for today. So, in order to characterize a univariate distribution, we need this function here. Well, in order to characterize a process, so Henry, you're looking forward to the recording. If I were you, I wouldn't listen to myself twice. That's equivalent to torture. Already once is hard enough. But anyway, you're free. So in order to characterize a process, well, what do you need? You need, so view on the left, there we go. So for the process, let's say T is in Z. What do we need? Well, we need the marginals. So we need these guys. We also need the joint marginals. Sorry. Because that would also be an important component of the distribution of the process. We also need the triplets. Etc., etc., etc. In order to describe the joint behavior of a process, we need these guys, these guys, these guys, and so on. All these functions are combined into what's called the finite dimensional distribution of the process. And it's what? Well, it's a collection of functions indexed in all the sets of this form, giving you the probability CDFs associated to the marginals with finite number of, well, to a finite number of marginals. So let's maybe say it better. In order to describe the distribution of a stochastic process, you need its finite dimensional distribution, which is the family of all functions of this form for any kind of index, any combination of indexes at T1 so for any n and for any combination of indexes T1 and Tn. So this is a gigantic family of functions. Well, it's a gigantic family of CDFs. So it's a gigantic family of CDFs. And this gigantic family of CDFs has a certain number of properties. For example, if I let y go to infinity in this guy, what do I get? Well, I get the probability that ft is less than x and that xs is less than infinity. Well, this of course is a certain it's an event which is certain, so this is just this probability here. Sorry, it's not an f, it's an x. In other words, the limit when I let one of the variables go to infinity of the joint function there, maybe that's better. So f of t s x y, it's itself so the limit of the joint behavior is itself a CDF. So that's one of the properties of these families, but there's many more. Well, maybe an easier example would be the case where they are independent. If the xt's do not have a joint behavior, if they're just supposed to be independent, well then the finite dimensional distribution is easy because all these FTs will just be the product of the marginal distributions. That's when they're independent. But in general, this is a very gigantic and very complicated family of distributions. And well, similarly as for random variables, to define a random variable, you just define its distribution. To define a random variable, you give the f. You give its CDF. And once you have the CDF, you're happy, because Skororod guarantees that there exists, so given an f, Skororod guarantees that there exists a probability space on which f is CDF. Well, it would be natural to define a stochastic process, and therefore also a time series, by specifying the finite dimensional distribution. There is just one small glitch in this theory, is that it is really not easy to show that for a given FDD there exists a corresponding stochastic process. In fact, it is not even trivial to claim the existence of an IID process. It is not even trivial to claim the existence of an IID sequence. That's how delicate this kind of stuff is. And as I was saying, we are saved by Kolmogorov, because he proved the following theorem. He proved that, and it's remarkably simple, he proved that a family of finite dimensional distribution functions defines a stochastic process if and only if, the thing we remarked on here, this thing here, is true for any combination of time points. If we have that condition, then we are guaranteed the existence of a stochastic process. I am obviously not going to do the proof of this result here. It's neither the time nor the place, and I think I never will do it in any class that I give. So, the simplest example of a non-trivial FDD would be the multivariate normal FDD, and this is the family of distributions constructed on the basis of the Gaussian density, which you all have to know, and this is the Gaussian density here. But of course there is many more. I won't be doing this here. We'll avoid using it. So what does this mean? It means that if you want to be able to construct a stochastic process, well, you simply have to exhibit a family of finite dimensional distributions which satisfy this property here, and if this property is satisfied, well then Kolmogorov's existence theorem guarantees that you are talking about something that exists. So yippee, we're very happy. We have a method of verifying existence, well, basically of verifying existence of IID processes and of Gaussian processes. Given these IID processes and Gaussian processes, well then we can afterwards define other processes by combining these. So for example, the moving average, which was obtained by combination. We could also take something of this form. We could also look at linear processes, but then once again, if we're looking at linear processes of which the autoregressive is just one example, again we have a problem because we are not sure that the summation gives an object that actually makes sense. For those of you who remember your math classes, you know that infinite series do not always make sense. I think we stop here for today. I think I've suffered enough. So end for 5th of October. Okay, there's a question here. Which of the textbooks you references is good for non-mathematicians to get up to speed with the mathematics we are seeing so far? Yeah, so the references, I forgot to do it, but it is my fault. I will put references on the UV and on the Teams. 3 or 4 books, and the ones you'll probably like best is the Shumway and Stuffer. That's the least mathematical of the lot, and it should give you a nice, a softer introduction. And if you combine the Shumway and Stuffer with my notes and my course, and if you're not mathematically inclined, well, just bear with me through these parts here, because there are parts that are much more accessible. So I know that this section here is rather technical because it discusses finer points around some complex ideas. You can literally survive through this course without understanding this. So don't worry too much about this last section. But the previous stuff that we did, so all the things that were before, well, yeah, that you will need, but that will be introduced in the Shumway and Stuffer. And I think the Neusser is quite nice as well. Brockwell is much tougher, so you probably won't like that much. Okay, so we stop here. It's going to be fine. I mean, you will succeed this course. I mean, succeeding is not an issue because the exam will be designed in such a way that anybody who does some serious effort will be rewarded with a pass grade. So you could literally just sit back and relax, but you will get. I mean, the objective is to learn as much as possible and to come out of this with as much knowledge as you can. So bear with me for the harder parts, and just if you're stuck, ask me questions and I will help you. Okay? So if everybody's happy, I'll see you next what? Next Monday. Next Monday around the same time. Have a good week. I'll put the stuff up maybe even tonight, yeah. I think I'll put everything up on the line tonight or tomorrow morning at the latest. If you have any question, contact me by Teams. Send me an email, and if I don't answer, I will answer. Okay? Good evening.
Perfect. Thanks a lot. Cheers.
Cheers, bye.
Thank you.
Bye, good evening.